Hello, today I'm going to talk about the interference of waves from two sources. So again, assuming now we have two speakers, spaced by exactly one wavelength apart. So the distance between these two speakers is the one wavelength apart, right? And then assuming the sound waves are identical, so meaning that they have the same sound source whose wavelength is the same, right? And then the waves will travel on top of each other, right? So the red speaker sound travels like this, and the yellow one travel like this way. So the superposition of these two waves, you have a larger amplitude everywhere, right? So the superposition says that for every point along the line, the net sound, which means the sum of two sounds, will be the sum of the pressure. So basically, you have a constructive wave here, right? So in other words, we call it in phase, right? So waves that are in phase will have a constructive interference, right? So the superposition is a traveling wave with a wavelength lambda and then twice the amplitude because you simply add the two same waves, right? So the most important thing here, in this concept is the path length differences, right? So two waves will be in phase and will produce a constructive interference anytime their path length differences is a whole number of wavelengths. So for example, instead of a one lambda differences, let's assume speaker 2 is located here and the distance between these two speakers, let's say is a 2 lambda. And you still will have a constructive wave. Because anyway, why? Because this one, good, and then this one, and then the new wave will start here with the yellow wave as well. So the same for the 3 lambda, and same for the 4 lambda. So we only care path length differences here, as long as the is in phase. So then you will have a constructive wave there, right? In other words, another case is called out of phase. Out of phase is that the sum of two waves is always zero at any point. And then this is called destructive wave. Condition for out of wave is a half-length differences. So in other words, two wavelengths will be out of phase and will produce destructive interference if their path length differences is a whole number of wavelengths and half of a wavelength. Okay? So the picture here is not clear, right? Because this is in phase picture, but let's assume uh, the speaker number 2 is located right over here. So then half wavelength differences. So then what happened here is that it will start like this way, and then right here we will go that way, and then we'll go this, right? So ignoring the red wave here, and then you see it's the red dotted wave is always opposite to this yellow one, and then they cancel each other. So that is called destructive interference. The condition is a whole wavelength plus another half wavelength. So the constructive wave condition is what? Path length differences is what? M times a lambda, where m is 0, 1, 2, 3. If m is 0, that means the path length difference is 0. That means the two speakers located at the same position. If m equal 1, path length differences. Again, definition of a path length differences is what? Basically the distance between these two speakers for this case, right? So if m is 1, this is the case, right? If m is 2, this is the case. And if it's m equal 3, it's gotta be here, 1 lambda, 2 lambda, 3 lambda differences, right? And then destructive interference condition is what? Again, m plus another half wavelength. So for example, if m is 0, so that means the delta D is 1/2 times lambda. So that means that this is a speaker 1, having lambda for each, right? Another lambda. And the speaker 2 is gonna be half lambda away. So that, its wave start from here, and then it has waves like this so that they can cancel each other, right? So then now we have two speakers emit sound waves with the same wavelengths. So basically you see these two speakers are identical, and then the waves are shown, displaced, but assume that both are traveling along the same axis, right? So the right here, what happened? So you see here the lambdas are 2 meters, right? So then this one will travel 2 meter, and then path length differences here is what? 1 meter. So the delta D is 1 meter, which is what? M plus 1 half, sorry, the times up lambda, right? So then this is a M equal 0 case. If M is 0, lambda is a 2, so the path length difference is 1 lambda, is a half wavelength, right? So your wave is going to be destructive, right? And then similar question, you have two speakers, right? Same thing. Which of the following could cause there's a destructive interface, right? So now this case, we have to interpret, investigate this case first, right? So now this is different from the previous case. Now our lambda is 1 meter and the path length difference is 1 meter. So basically we have a constructive wave, right? But in order to make this one, destructive wave, you have to make this distance, path length difference is either 0.5 meter, which is a half of it, or 1.5 meter is also fine as well. So the answer is B and C. You can either move right one, speaker 2 to the right or to the left. Doesn't matter, right? Both cases will give you destructive wave. Again, Sujan stands directly in front of two speakers that are in line with each other. The further speaker is 6 meters from her. So now this is a 6 meter. D1 is actually 6 meter. The closer speaker is a 5 meter. So this is a 6 meter. This is a 5 meter, right? So the speakers are connected to the same hertz. So basically these two speakers are the same, right? And the Sujan hears the sound loud and clear. So what does that mean? This is a constructive wave is now formed, right? So the frequency of the source is slowly increased until at some point the Sujan cannot hear, the constructive wave anymore, right? What is the frequency when this cancellation occurs? So basically here we increased a frequency, right? Assume the speed of sound is 340. So then now, basically what we can say here, based on this sound wave source, right? What is a lambda here? First step, you gotta find here is the lambda of the source, right? So your lambda, your velocity of sound wave is what? Distance, lambda, times a frequency, right? So that means your lambda is a 1/2 meter, right? Which is a 0.5 meter per, 0.5 meter, right? Right. So this is a lambda is a 0.5 meter, right? So this is the first, fact we have now. So instead of velocity, we now know lambda is a 0.5 meter, right? So then now you see the speaker 1 and the speaker 2 is 5 and 6 meters away. What does that mean? That means delta D is 1 meter, but the path length difference is 1 meter, so your lambda is 0.5. So then you can see why Sujan has a constructive wave there, right? So then, yes, this is what it means. Your delta D is 1 meter, and then lambda is a 0.5 meter. But now, because we will change the frequency, right? So the lambda will be changed as well. Okay, so that's what we're going to do here, right? And then you can also see m will be 2, right? Because why? Delta D is a m times lambda, right? So delta D was actually 2, what was the delta D? 1 meter, right? So we got that. Delta D is a 1 meter equals lambda times a, lambda was a 0.5 meter, and then so m is a 2, right? So then now you see m is a 2, right? So we see that m is a whole number as expected for constructive interference, right? As the frequency increases, and then the wavelength will be decreases. Why? Because the velocity, speed of sound, 340 is a constant always, right? But this is a lambda times the frequency. So if you increase frequency, then wavelengths will decrease, right? Right. So then our initial lambda, next one is gonna be destructive, constructive wave, right? So then our delta D still never change it. So then now m value, but this one is gonna be 2.5. Why? Because our m is a 2 here, but lambda, what is the next to destructive wave condition after m is a 2? Destructive condition is what? Delta T is a m plus a 1/2 times a lambda, right? So in other words, this value, because our m is a 2, right? So this will be 2.5. So then this is a 2.5 times a lambda. So that means our lambda is going to be 1 divided by 2.5, which is a 0.4 meter. So then now you see frequency is going to be 0.4 divided by 340 divided by 0.4 will be 850 hertz, right? And then, here so far we assume the sound wave travels along the straight line, right? But the attached question is, what if the sound wave travels, in three-dimensional space, right? So, but basic idea will be the same. This is a, sound wave source, and then you have one full wave, right? So this is you have where you have a first crest, and then another crest, and then another crest, right? So this is where you have lambda, another lambda, if you assume this is a straight line, right? So then now let's assume we have two speakers, but now we assume the waves travel along in three-dimensional space. For example, now think about what happened at this red dot. You have a lambda, lambda. So what is the speaker, the distance that speaker one travel? Basically it travels 2 lambda, right? The sound source from the speaker one travels 2 lambda, right? And then how about the sound from the speaker two? 1 lambda, 2 lambda, 3 lambda, right? So then now speaker 2 have a 3 lambda trouble. So then now it's a 2 lambda trouble. So what is the path length difference? Is D. That's simply 3 lambda minus 2 lambda, which is 1 lambda. So then now you see here you will have a constructive wave, right? Because it's a whole number of lambda, right? For example, what happened here? Again, 1 lambda, 2 lambda, 3 lambda. R2 is what? 1 lambda, 2 lambda, and 0.5. So the path length differences is a 0.5 lambda. So this is the position where you have a destructive wave, right? Again, the condition is same. Delta R is a 1 times lambda for this case. So M is 1 case. Then you have a constructive. And then if your path length difference is a half lambda, so this case, if I rewrite it 0, which is M0, 1/2 times lambda, so then you have a destructive wave as well, right? So then again, same condition, right? So then now we can talk about this position, and then what is the path length for the source 1? 1 lambda and half lambda. So the path length for the source 1 is a 1.5 lambda. And then how about 2? The blue one, 1 lambda, 2 lambda, and half, right? So the second one, path length is a 2.5 lambda. And then the difference is between those two is a 1 lambda, so you will have a constructible wave. Okay? And then similar question, right? So then now you see R1 is a 4. So this is 3, 4. So then you see clearly R2 is a 5 meter using the Pythagorean theorem, right? And then now you have the very first thing is you have to find the path length differences. For example, you have a Sam here. So the speaker 1 travels 4 meter. Speaker 2 travels 5 meter. So the path length differences is 1 meter here, right? And then the frequency is 170. So that means your velocity is 340. So your velocity again, 340 is lambda times the frequency 170. So for this case, your lambda is 2 meter. But path length difference is 1 meter. So you will see you will have a destructive wave, right? Right? So, and then next topic is about the beat. Okay, so the beat is nothing but the principle you use when you tune your musical instrument, right? For example, you play two different sound source at the same time. Then what you're gonna see is at some point the waves are in phase, so you have a higher sound, and at some point your waves are destructive because they are not the same sound source, right? So then now you see your frequency is not only oscillating in terms of magnitude, right? So then you see the magnitude of the combination of the sound source also generate another waves, right? So that means the actual F oscillation frequency, that's about this blue wave, right? So then you see here there are two different waves here, right? The blue wave here, that is based on frequency oscillation. And then you also have another frequency called the beta frequency that is based on this brown wave. So then you see what this brown wave actually means here. Your sound itself is a very loud low and loud low and loud low. But what F oscillation actually means is boom 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 sound variation itself. Okay, so then we call this one is a bit frequency. Okay, so you have a two formula that you can solve this one for your homework. Okay, you have a two different type of frequency. One is the average of these two waves, and then the other one is based on the differences, right? So then now you two speakers emit sound nearly equal frequency, but slightly different, right? So then again, as shown here, right? At point the two speakers, the sound varies from loud and soft, right? So here it says loud and soft. That means that this is about the blue wavelengths, right? So how much time release between two successive loud movement? And then you have a frequencies, bit frequencies based on the differences here, right? So the bit frequency here is 1. So then you will hear one sound, right? And then you hear 2 beats per sound per second when the two sound sources both at rest, play simultaneously. So 2 beats, what does that mean? They both have the differences between these two frequencies are 2, right? So in other words, f1 minus f2 absolute value, because we don't know which one is greater, is 2 hertz, right? And then the beat disappear if the source 2 moves toward you. So then this is a Doppler effect, right? If the source to this one source is moving toward you, then what happened? Its frequency will increase, right? And the source 1 remains rest, right? The frequency of the source is 1 hertz. And then what is the frequency of the two source? So then the answer, you can either have 2 higher or 2 lower, right? But the beats disappear. The beat disappear means the second source is moving toward you, right? This bit frequency will increase. So at some point it reaches 500. So the answer is B, right? So another example is, sometimes we human has the range of hearing, right? So, but, some bat like, brown bat has a common, it's a common in North America, and then it emits frequency sound of a frequency which is 40 kilohertz, which is really big, above, the range of a human hearing, right? To hear, basically this sound, you don't need to directly hear it, right? But you cannot hear it, so you have to generate another bit frequency, which is close to 40 kHz, right? So then you can see the beat frequency, loud sound, low sound, loud sound, no sound, right? Instead of directly hearing this sound, right? So then the result frequencies are also related with the filter, right? And then bit frequency is 3 kilohertz. So then what do you need? Because the original sound is 40, bit frequency is 3 kilohertz, and you can see you can either have a 37 or 43. Okay, this is the end of the chapter 16, and then I will upload your next homework, okay? So due sometime next week. And okay, thank you.